Hi, so the first speaker for the last session is Uddeepta, and he'll be talking on microlensing of gravitational wave signals, effects of the uh, galaxy lens.
Hello, am I audible at the back? Okay, good afternoon and welcome back. At the outset, I would like to thank the organizers for putting up this effort and for allowing me to speak about our work. So the title of the work is, as you can see, Microlensing of Gravitational Wave Signals, Effect of the Galaxy Lens. So as the old saying goes, lensing of gravitational waves does not only give you multiple images, also gives you multiple talks. So just like Ankur presented a few minutes back before me, so I would be talking about a little bit different aspect of gravitational lensing. Hope you would be able to you'd be able to understand, and I should be able to make it clear for you guys. Stop me whenever you want. This work has been in collaboration with Ajit from ICTS, Apratim from Ayuka, he was at ICTS earlier, and Soham Bhattacharjee, who is currently at IIT Madras. Okay. So what is gravitational lensing and why are we interested in this? So as of here, you can see this is an image taken from the Hubble survey team. So you can see a couple of things here, like this kind of arcs here, right? These are produced because there is a strong potential, gravitational potential, which is sitting in front, in between the observer, which is us, and a source, which is a galaxy behind the lens. Okay, so because of the presence of a gravitational potential, what it does is it bends the light coming from the source towards us. Okay, so the bending of light, so to say in colloquial terms, is what is known as the gravitational lensing. Now, in gravitational lensing, you can also, so these two images or two or multiple images which come to you would always be separated by certain time delays. These time delays could go on over to months and so on, which Ankur had already explained. Now, in our talk, what I would like to focus about is a different aspect of lensing. But why we are interested in lensing, let's first come to that, is because in the coming years, there would be more and more, like millions of detections per year of gravitational waves. And with such many detections, you expect a lot of lensing events to take place. And with lensing, it gives you more feasibility to explore other physics, one of the applications of which I am talking about in this talk. So what we are focusing here is something known as the strong gravitational lensing. So gravitational lensing has different parts, of which the strong lensing is something like this. So this is the schematic of the thing which I just explained. So you have a source sitting here. There is a perturber or a strong lens which is sitting there in between the source and the observer. And you see that it acts as if there is a convex lens here. And that's why gravitational lensing. So in strong lensing, you are guaranteed there are multiple gravitational waves which come from the event. Now, there could be two regimes. One is when the time delays, which I just mentioned, between the different events is much greater than the inverse frequency of the gravitational waves you are looking at. So in this regime, we can work in the geometric optics limit. That means you can work in, let's say, in the saddle point approximation, and you can say that these are ray optics, rays coming towards you. However, in cases where the time delays are of the order of the inverse frequency of the gravitational waves, you end up in a something different regime. So this is what I will call as the microlensing regime, or the diffraction effects do take over in this regime. In case of light, the first one always holds, because in case of light, the time delays are much larger than the inverse frequency of the light signals. However, in case of gravitational waves, one could as well see these be in this regime. Now, the typical lens mass, which would create such effects, would be of the order of or less than 10 to the power 5 solar mass for 1 hertz of frequencies. Okay, so I hope the system that we are talking about is clear. So what exactly happens quantitatively in microlensing is the following. So if you look at this plot on the right hand side, the cyan or the bluish signal is the one which is a gravitational wave strain signal. This is the time series data. Okay, and this is unlensed, the blue one, while the red one, as you can see, has many more features. These features are obtained because of the microlensing effects. And these features are frequency dependent features. Unlike in the case of geometric optics, wherein you can just do away with a constant phase shift and a constant amplitude increase or decrease. In the case of microlensing, you will have frequency dependent features. And however, there is no evidence of microlensing in the gravitational wave signals detected by LIGO Virgo so far. And this non-detection of gravitational wave signals, microlensing signals, is what motivates us towards this particular work.
Hey, I have a question. Since you said we can stop you. So in the previous diagram, there seems to be even some intensity change. Is that some focusing happening?
In fact, yeah. So you mean this one?
Yeah.
Yeah, it does. So there is some intensity change. There is phase change also. So there is a phase dependent quantity as well. So this work is an extension of what Somadeep and others have done. So it's basically the following. So Ankur has already mentioned, you can constrain the dark matter fraction in the universe by looking at the non-observation of gravitational microlensing effects. Now, in this particular case, you neglect the effect of the galaxy because the dark matter itself is now your dark matter is sitting inside of a galaxy, but the galaxy effects need to be taken into consideration. So the work that which I am explaining is how much does the galaxy effect biases your inference about the fraction of dark matter, for example. And so this is kind of a cartoonish way of looking at things. So you have a galaxy in which the different dark matter halos are there. So you have, as of now, one can think of the dark matter objects as just compact objects which are isolated. But a substantial fraction lies in the halo of the galaxy, and because of the galaxy effect, it can introduce extra parameters in the amplification factor. What we call the amplification factor is the factor which changes this effect, which you are just saying. Okay, I'll just mention this. Okay, so this is one slide where I have just included some equations, but don't be afraid of it. And so this is the last one which I want you to focus on. Is basically, this is the unlensed waveform of a gravitational wave signal, and you multiply it with the frequency dependent amplification factor because of the microlensing. This is the resultant waveform is the lensed waveform, which you want to analyze. Okay. Now the difficulty in this particular work comes because of the presence of this external potential here. Okay. And this amplification factor is nothing but an integral of this kind, wherein the integral depends on the value of this time delay function. Okay. And this time delay in place depends on how the lens is modeled. In our case, the lens has an external potential sitting in there. Okay. So interestingly, these kind of models you cannot solve analytically completely, but also there are challenges even in solving it numerically. So I'll quickly. So how do we solve these actually numerically? Because analytically it's not solvable. Only for one particular case it's solvable, which is the isolated point lens case. If you take the amplification factor in the time domain, or in fact the amplification factor divided by the frequency, by the way W is the frequency, then in the time domain it looks something like this. It's just a delta on the time. So what it motivates us is to basically consider this as a ratio of the areas between two close by time delay contours, okay, separated by delta t. So if you take this ratio, it essentially gives you the time domain component of the amplification factor. Now, in order to go to the actual amplification factor, you just need to do an inverse Fourier transform and then multiply with the lens signal. It's a simple step. So our work, we propose a different way of, so there are some existing methods of computing this amplification factor. We propose a different way, which we expect to be more accurate, more flexible, to include many more lens types. And also it gives you a computation in much faster time. So what we do is we basically grid the time delay contour. So if you look at these contours here, so colors denote time delay values. So any two closed by contours would give you an area between those closed by contours. This area is the ds factor in it. Okay. And you want to know what is the dt factor, which is the time delay difference between these two closed contours. So in order to do that, you just grid this plane into multiple smaller grids and take the histogram of the time delay values that you obtain from those grids. So you evaluate the time delay at this grid, take the histogram. This basically gives you something like f tilde t, the time domain amplification factor. Okay. So here's the plot, which so in the time domain, the f tilde t looks something like this. So this is, for example, what I'm contrasting here. So what I'm contrasting here are the values when you just have a dark matter, say compact dark matter object, which is the blue one, and when you include the effect of the galaxy, right? So the galaxy effect can be incorporated by introducing this kappa value, which is in technical terms known as convergence factor. And as you can see, there are additional features in this time delay function. Now, if you do an inverse Fourier transform and look at it, then these are the kind of different, sort of lens signals that you might observe. So this is just a qualitative way of understanding what happens when you introduce the galaxy effects. A more important way of understanding these galaxy effects is by looking at the mismatch values. So what are mismatch values? You take two functions, one function wherein you do not have any galaxy effect, the other function where you have the galaxy effect, and you integrate them over the frequencies in the frequency domain, okay? And you normalize them, and also weigh in by the detector response. That means the detector noise. So this particular thing is known as match, and 1 minus match gives you a mismatch. Okay, so consider the y-axis to be, so higher the value of the y-axis, more is the effect of the galaxy lens that you want to take into account. So for example, if your lens, sorry, this is cut off, but these are lens masses, 100 to 10 to the power 5 solar masses in which the microlensing effects take place. So as you can see above, so there is this -3, which is 0.1% line. Above this line, all these values, you need to take into account the effect of galaxy lens. Okay, so if your lens masses are in, let's say, 10 to the power 3, and you are at an impact parameter sitting at around 0.1 away from the lens, then your galaxy does play an important role, and so on. So okay, I'll conclude. So as a conclusion, so non-observation of microlensing of gravitational waves, as can be seen, constrains the fraction of dark matter in compact objects, which Ankur and Somadip's work clearly indicates. With increase in the detections, better are these constraints. However, the effect of galaxy or external potential will be important in certain regions of the lens parameter space. And this introduces a bias in the estimating the parameters of the source from which we are getting the lensed signals. So we do need to develop tools for fast and efficient ways of doing a parameter estimation of general microlens signals. And this is one of those applications which, one of the applications of the tool that we are currently developing. And we can also search for exotic gravitational lenses. In fact, one of our projects include looking for charged lenses, charge in the galaxy, in the lens which is there. And all these things can, enable us to do a better parameter estimation and a faster parameter estimation, the whole method. So with this, I conclude, and I'm open for questions. Thank you.
Thank you, Uddeepta. Any questions from our audience?
I can go ahead. Right? Yeah. Can you go to the third last? Yeah, one more. Yeah. So why is the impact parameter, right?
Sorry?
Why is the impact parameter?
Why is the impact parameter? Yeah.
So impact parameter for the small lens.
Small.
So if the impact parameter is large, it means that the effect of the small lens should be smaller.
Effect of this?
Of the micro lens should be smaller.
No, sorry. So why being large would mean the, okay, it is larger, but then there is galaxy as well.
Yeah, so the galaxy's effect in comparison to the micro lenses effect should be larger if the Y is large. So why are you not seeing higher mismatches for higher Y?
Okay, so these are, first of all, these are like just preliminary results, and also, so you mean you wanted to have higher mismatches here as compared to the previous
left-hand side plot.
Right, but then I think it will subside over the lens galaxy lens. So here we have considered a distribution of this k versus the location of the lens, location of the micro lens. For example. So I should be able to answer this better. I'll have to check.
Thanks.
Yes, Shalabh.
I have two quick questions. First of all, in your model, you are assuming that a lot of dark matter halos reside in a galaxy. Is it true?
So so that is the final aim, to look at what is a fraction of dark matter that you get biased because of non-inclusion of the galaxy effect. But as of now, this is just by taking let's say one dark matter particle or one dark matter lens and see how the galaxy affects on it.
Okay. Okay. My naive understanding tells me that maybe isn't it the reverse? Like one galaxy stays inside a halo.
Oh, that is the halo of the dark matter. But here we are looking at compact dark matters, compact objects.
Okay. Second question is, you get some amplitude and phase modulations because of microlensing, right?
Yeah.
But you also get similar modulations because of spin and eccentricity effects. That's true.
Because of spin and eccentricity, yes.
So do you know how to distinguish between them?
So you need to do a similar mismatch calculations if you want to look at the degeneracies between the spin or precession, for example. So there have been works where people have looked into precession versus microlensing degeneracies.
Okay, so there are standard methods, right?
There are not standard methods, but people have looked into it.
Okay.
Yeah, not well established yet.
Okay, Loga, one more.
I had two questions. So one, like regarding this pictures that you had of how the lens signal and unlensed signal look like in the waveform. So what is the kind of parameters that you're assuming here? I mean, like, because these seem very,
very different.
You're saying there will be so much change. So what is the...
So just by looking into it, if you just look at it, so these are the kind of parameters which I've chosen.
Okay, so what, could you just say this y is of what, like?
Oh, sorry.
So you're assuming 300 solar masses for the lens.
Correct.
Okay, and
y is the impact parameter, which means how much, so you have let's say 2D plane on the sky, and you have a lens somewhere. How much of the source is away from the lens? That gives you the value of y on this 2D plane, projected 2D plane.
So this is in what units? It's 0.5.
Yeah, so there is the unit is Einstein angle or the Einstein radius. So it's basically, it goes as root over m of the mass.
Okay, so for example, like this much amount of lensing, how many events do you expect? Let's say, I mean, I'm just trying to say,
right.
Is lensing really so prominent in most events, or like what is the...
I cannot quote the exact numbers from here, but the distribution of y is basically the distribution of y is linear in y. So in fact, yeah, it goes linear in y. So the number of lenses would keep on decreasing as you go away from it, because it goes as r square. But so also the effect will keep on decreasing if you go much away from it.
Okay. So another unrelated question. So when you say when you are saying that like it's difficult to do numerics on this integral and so on, why is it difficult to just directly do the numerical integral in that case?
First of all, this numerical integration. Okay. So this one, for example. So so you have three independent variables here: x, x1, x2, and w. x1, x2 are the lens planes, and w is the frequency. So it is very highly time consuming. Also, you need to have, so the integration should converge because you have a finite domain integral. If you want to do it numerically, there are other issues which come up, is that the existing methods, they need to solve two sets of ODEs to go through these, the time delay contours which I just mentioned. So what you do is you place your point somewhere on the time delay contour and you revolve around this contour, and you expect that the point will come back to the original position. So that's an innate approximation assumption. And if you want to solve these two ODEs, it takes huge amount of time. Also, this approximation might break down at certain points. Thirdly, third issue is that the potentials which we assume are usually singular at some point. So there are singularities. So for example, in this particular case, you have a log term here, which might give you absurd results. So in ideally, there will be n number of lenses, which would give n number of such singularities. And so this increases your difficulty.
So the claim is that if you go to the time domain and do the integrals there and then you come back, it is better.
Yes.
Okay. Okay. Thank you.
Okay, let's thank Uddeepta.